morning. Today we're exploring how data is stored on Stellar's Soroban smart contract platform and what developers need to know about Soroban state management. Blockchain technology has come a long way from Bitcoin's seminal design with 10-minute block times and very simple transactional data. Today, Web3 developers like myself write code that is coming closer and closer to resembling back-end server-side logic. This requires faster confirmations and more data storage to enable our decentralized applications to perform efficiently. As we push the limits of decentralized computing, a problem emerges. On many smart contract platforms, every single transaction, every token swap or NFT purchase, every single piece of on-chain data is stored permanently by every node on the network. This data grows and grows over time into what we call state bloat, which burdens the validators with ever-increasing costs, and it takes away some of the network efficiency and scalability. Soroban tackles this issue head-on by making persistent storage subject to a rental fee. Developers prepay rent for their contract's code and data storage in the native XLM token. As time passes, you can extend its time to live by topping up the rent. If rent expires, then the data is moved to an off-chain archive, and if you need that data back, you just pay the rent and it's restored on-chain. The state archival system uses a Merkle tree structure for verification and making data restoration secure and reliable. Developers can at any time restore their archived contracts and data to their original locations by topping up the rental payments. This solution effectively prevents stale data from clogging up the network and creates a sustainable, efficient blockchain. Let's dive into some code. Soroban provides 3 primary storage types available within env.storage, each tailored for a specific use case. Persistent storage. This storage type is designed for data that needs to remain accessible over extended periods. While persistent entries might expire and be removed from the ledger, if they deplete their rental balance, they can be restored and they cannot be recreated. Their behavior makes them suitable for critical information that requires long-term retention, such as token balances or ownership properties. Temporary storage is ideal for data that is short-lived or can be easily recreated. Temporary storage is more cost-effective than persistent storage, and entries in temporary storage are removed from the ledger after their designated lifetime ends. Instant storage. This storage type is tightly coupled with the contract's instance and is suitable for small amounts of data that is directly associated with the current contract, such as admin configuration settings or the tokens that a contract is operating on. The amount of data that can be stored in instant storage is limited by the ledger entry size, and it's in the region of about 100 kilobytes. Within these structs, we have the following methods. Has is used to check if a key exists, returning true or false. Get is used to fetch a value by passing in the key and returning an option. Set is used to set a value to a key. Update is used to update a value stored against a key. Try update is like update for those times when you don't know what you're doing. Extend TTL extends the time to live for data stored under the key. And remove removes a key value pair from storage. When writing Soroban smart contracts, it's essential to choose the appropriate storage type based on the data's nature and lifespan. Let's look at a practical example of how we can store some persistent data, writing our name on the blockchain and then extending the TTL so that we live long time. So this code is all on GitHub. You can find it at jamesmachini/Soroban-data. If we go into contracts, you can see we've got this source folder and then we've got lib.rs. Let's open this up in VS Code. So we have a pretty standard contract, and then we've got 3 functions here. We've got pub set, which is taking a symbol for the key and the value. A symbol is a short string, and we're setting that to persistent storage, instant storage, and temporary storage. So you can see the methods for all 3 of these is very similar or exactly the same. We're passing in a key and a value, and we're setting data to that storage type. We then have a public get function which takes a key and this goes out and fetch the data. We're using persistence data here, but we could just as easily change this for instance data. Persistence and instance data have the same cost, it's just the instance data is kind of integrated into the contract, and it also has a limited capacity, and that's something to be aware of from a security point of view, because if you enable your users to update that instance data, they might be able to create a denial of service attack where they just store more and more data in that variable until you reach the limit, and that creates a denial of service for the contract. We then have this extend function, which we can call to extend the time to live for that data in the contract. We get the max TTL available using the m.storage, and then we set the persistent data to extend TTL for this key. So this is the key that we're setting in this line here. And we're passing in the max TTL. This is actually the minimum TTL that you could run this for, and the max TTL here. We're using it for both because we're not too concerned about that. And the same with this one, we're increasing the instance storage for the entire contract. This is the contract code and the instance. If you want to deploy this to the network, let's fire up a prompt and we can build the contracts to start with. We're using cargo build target WebAssembly, and we're setting that to release. Once that's built, we can run Stellar contract deploy. I'm going to deploy this to the testnet. And if that's successful, it should give us a contract ID, which is this CC variable here, an alphanumeric string. Now let's try setting the variable. So we're going to set the key name to the value James Bacchini. That looks to have gone through. Let's just double check by calling getName. That's returning James Bacchini. So we stored that value on the Soroban testnet. And the final thing I want to do is increase the time to live. So let's go ahead and run extend with the key name, because we're passing that in. And that's how we can extend the life of our contract and data. If we go into the developer docs at developers.stellar.org, we've got this information about restore footprint op. And if our data did get archived using either the persistent or the instance storage, we can restore this at any time. And there's an example of how to do this running this code here. Ready to start building? Then check out the blog post linked to in the description for complete code examples and detailed guides. Don't forget to like and subscribe for more Soroban development content, and thank you for watching.